In this video, I'd like to talk about leaving groups and specifically what is it that makes a leaving group a good leaving group. And we're talking about this in the context of nucleophilic substitution reactions. So just to reiterate, we're really sort of talking about this. And this is sort of an SN2 reaction where we do this. And what we're really interested in is this. Now, if you've studied organic chemistry at an undergraduate level for any length of time, what they'll typically tell you is that a good leaving group is the same as a weak conjugate base. But they never really explain why that is. And so I think we can sort of bypass this explanation. This explanation just means, okay, what is it that makes a weak conjugate base a weak conjugate base? So why don't we not worry about what makes something a weak conjugate base and just worry about what makes something a good leaving group? And the answer is basically how stable it is after it leaves. That's what determines whether something is a good leaving group or not. And that's also what determines whether something is a weak conjugate base or not. The weak conjugate base is very stable after it gets deprotonated. And there's 4 considerations, and these considerations are very much likely to be found in any discussion on what a conjugate base is. And the first is electronegativity. The second is resonance. The third is atom size. And there's a fourth, which you're not going to find in any discussion on weak conjugate base, which is bond strength. Okay, so let's go through these by combining them in some sense. And the first one I want to look at, there's a type of leaving group that combines both 1 and 2. So it combines both electronegativity and resonance. And this is a kind of leaving group that's very, very good. And I'm talking about things like Tosyl and Mesyl. So we'll look at both of these. So let's imagine the same SN2 reaction that I showed above. This time we'll actually show a concrete electrophile. And let's show Tosyl. Toluene sulfonyl is what Tosyl is. So here we have Tosyl. And here we have our electrophilic carbon. Our nucleophile comes in, attacks it, and displaces the leaving group. And so we can show our product, nucleophile. We have alkylated our nucleophile, and we've displaced this group right here. Now, it should be pointed out that this is indeed a very weak conjugate base. Why is it a weak conjugate base? It's a weak conjugate base because this lone pair on the oxygen is really not available to pick up a proton. Why is it not available to pick up a proton? Well, it's for the 2 reasons that I showed above. One is the electronegativity of the atom, which is one of the principal components you'll learn about when we talk about acidity and basicity. An acid is usually something that's very electronegative, and the proton almost falls off of it, right? Because it's electronegative, it doesn't pick up a proton, and also because of this resonance contribution with the neighboring sulfonyl group, and we can show that resonance contribution. There's actually 2 resonance contributors we can show, one with either S double bond O, but I'll just show the one. So we have an electronegative atom and resonance stabilization. So in other words, when this leaving group leaves, when the Tosyl group leaves, it's stable. And that's the same reason it's a weak conjugate base. It's perfectly happy without the proton. So we can say it's stable. And that's why undergrads will usually be taught that a weak conjugate base is the same as a good leaving group. Well, they're similar. So this is the first type. And I mentioned Mesyl as well, so I guess we can show Mesyl. So this is Mesyl. It's going to really be very much the same kind of chemistry, this time with a methyl group. Okay, so here's our electropositive electrophile. Nucleophile attacks, displaces this. We get our alkylation, of course, plus the mesylate leaving group. And of course, this is stable. It's stable for the same reasons as, that I've articulated above. It has an electronegative oxygen atom, and it is resonance stabilized with the neighboring sulfonyl group. So a good leaving group is something that's stable. Now, there's a second kind of leaving group that you're going to see very commonly, and I want to really articulate something important about it. This is really sort of going to be, so up here we have a combination of electronegativity and resonance, and the other kind are the halogens, and these are a combination actually of the other three. So they're a combination of electronegativity, atom size, and to some extent bond strength. So let's think about the halogens. I'll draw the whole group. And we have fluorine, chlorine, bromine, and iodine. There's actually astatine as well, but we won't bother with that. So it's not quite the whole group, but it's the atoms that sort of matter in this discussion. Now, if we rank these in terms of their capacity to perform as leaving groups, iodine is the best. Then bromine, then chlorine, and finally fluorine is the worst. Now, this might seem counterintuitive because let's imagine we have a nucleophile, and let's take this electrophile, and we'll take this electrophile. Now, the fluorine is far more electronegative than the iodine, far, far more. They're both pulling in the same direction and leaving behind a very electrophilic carbon atom that can be attacked by the nucleophile. But the fluorine is so much more electronegative than the iodine, so you might expect the fluorine to be a much better leaving group. After all, fluoride has an extra electron, and fluorine should be very happy with that. It's very electronegative. And iodine is less electronegative. So why should it be happier with the extra electron after it leaves as the anion? Well, there's an answer for that. We'll draw the attack. And there's two answers actually. The first is bond strength. This is a consideration. The carbon fluorine bond is a very strong bond actually. So that's the first consideration, but I don't think it's the most important consideration. The most important consideration is the atom size. Fluorine is an atom with 9 protons, and iodine is an atom with 53 protons. And what this means is when the fluorine atom gains another electron and becomes an anion, it now has 10 electrons, right? It's going to have that one extra electron. That's why it has a negative charge. And there's one extra electron per 9 protons. So you have an atom with a nucleus size of 9 stabilizing one extra negative charge. So we can say 1 per 9 protons. Now, iodide has 54 electrons if it's negatively charged, right? An anion, it has one extra electron, that's 54. And we can say that for iodide, there's one extra electron per 53 protons. So for iodide, it's much, much easier for that one extra electron to hide out in the electron cloud, you can say. The nucleus of 53 protons is sufficiently large that accommodating one extra electron is not that big of a deal. It's only 1 per 53. So the size helps the atom accommodate the one extra electron. With fluorine, however, there's only 9 protons actually. So if you add one extra electron to generate the anion, that's quite significant. That's a 1 per 9 ratio. And so for the halogens, you get the ranking like this. Iodide is best, fluorine is the worst for a leaving group. And these are the reasons. Electronegativity, of course, all 4 of these atoms are electronegative. They would have to be if they're going to operate as leaving groups. They have to sort of pull toward themselves for them to leave as a leaving group. So they have to be electronegative. Bond strength is a consideration. Obviously, the bonds decrease in strength as you go down the table, and that's very much significant. But the atom size actually is a very important consideration here. And so for ranking the halogens as leaving groups, I would say the atom size is really arguably the most important consideration because, as you can see, accommodating the one extra charge is going to be much, much easier for iodine than fluorine.